But let's consider another daily life problem, which is the case of floating solids. I mean, maybe some of you are like sailing. Oh, I'm sure that all of you have some time traveled in a ship, okay? What is the fundamental of stable floating for ships, for instance? Imagine that this is the hull cask of a ship, simplified, right? Okay, it's floating. So it is floating, according to the principle of Archimedes, there is the resulting forces on the boundary of the hull is the upthrust force. Where is this upthrust force applied to? To the center of gravity of the displaced water. So let's assume that it's in that position, okay? What is the other forces that are acting on the ship? Well, the weight of the ship and everything that is inside. And this is a force, W, which is equal to E by the first part of the Archimedes principle. But it's applied on a different point. In what point? In the gravity center of the solid. Okay? So we have the upthrust, which is applied to the gravity center of the displaced fluid, and the weight, which is equal in modulus to the upthrust, but applied to the center of gravity of the solid. They are not the same. They don't need to be the same. In general, they shouldn't be the same. So, okay, that's in equilibrium. Okay, that's an ideal situation. But imagine that now we introduce a little perturbation that moves a little to the right, for instance, the floating ship, for instance. Okay? What happened in that case? Well, the forces are going in equilibrium, so this upthrust force and this omega are always the same, but due to this perturbation, the gravity center of the solid, of the displaced fluid, the buoyancy center, moves a little bit to the right, okay? Whereas that one probably keeps in the same position. But what is the difference now with respect to this ideal solution? They are no longer aligned. So this force and that upthrust force are the same. But they are not aligned with each other, okay? So what happens? There is the second part of the equilibrium of that there is a recovering moment that is the moment produced by this force to the down and this force up force that tries to what? That moves the ship is a moment that, in that sense, that tends to recover the original position. Okay? So, what happens if you are in a ship, in a boat, and then you just put some perturbation that moves the boat, so it moves and then it recovers, and it does like that. It does like that, right? Remember that you are, this matches your perception of what's happening in a floating solid, right? When you try to perturb it, the position, there is something that makes it to recover the position, and maybe after recovering, then it goes to the other side, and then also recovers and so on. Okay, that is a situation that we have considered in which the center of gravity of the solid is below the buoyancy center. So that moment is a recovering moment, right? It's a moment that tends to recover the original position before the perturbation. But what would have happened if instead of that, by some reason, the weight of the solid, the center of gravity of the solid here, and the center of gravity of the displaced fluid are in that position, the first above the second, okay? Of course, they are equal to each other, and this position is in equilibrium. There is no moment, forces are aligned, and there is no resulting forces. This force cancels that one, okay? But what happens after a perturbation like that? When we perturb, this point moves to the right, These points move to the left, and then there is, of course, a moment, but now the sense of the moment is the opposite. It's in the sense of the tipping, okay? It's in the sense of the perturbation, so just increases. This moment is larger and larger and larger, so finally it turns to a low water entering here and sinking the boat or the ship or whatever, okay? So look, if we wanted to design a ship, so look, every naval architect is aware of that. In order to get the maximum stability of a floating boat, we have to place or to put the center of gravity of the floating solid as much as possible below the center of gravity of the displaced fluid, in order to be that situations and never get that. Okay? So why do we do that? Well, instance, by introducing additional weights at the end, at the lower part of the ship, okay? In order to lower the center of gravity of the solid. That's what is called lastre, okay? If in a ship, I mean, this ship that we see sometimes, carrying a large amount of containers, so the containers, which are the loading here, just raise the center of gravity. So they have to be very careful in that the resulting center of gravity is below the corresponding center of buoyancy. Otherwise, the ship is not stable. And when the waves are acting in the open ocean, then the ship would become unstable and turn over and sink. Okay? And that's something that type of, the lower is the center of gravity, the center of buoyancy. No, sorry, the lower is the center of gravity, the more stable is the ship. That is why, for instance, in competition, in competitive sailing, so we know what you have in here in very competitive, we have additional weight here, which is the bulb. What is the role of bulb? The role of bulb is lowering the gravity center in order that then the ship can remain inclined but stable. Inclined but stable. That's something that we have to design, but of course you have to be in balance, to keep that in balance with the hydrodynamic conditions of the ship. So I mean, that is just the science of naval architecture. Okay. So now it's something, the simple application of the Archimedes principle.